So review topic 6 is all about the atom, its structure, its history, and we're also going to briefly touch on atomic mass calculations. It's really going to help you to have a periodic table to do this part. Just to review, protons, neutrons, electrons, atoms, ions, isotopes, those are all terms you should be familiar with. Protons and neutrons are both found in the nucleus. The electrons are found outside of it, localized to the orbitals. Protons are positive, neutrons are neutral, electrons are negatively charged. Protons and neutrons are fairly large compared to that of an electron. Protons are really important because they help you identify your element. That's via the atomic number. Neutrons help us distinguish between the different isotopes of our elements using the mass number. Sorry, my cat decided to walk over here. And then electrons help us distinguish between atoms and ions. When you have equal numbers of protons and electrons, you are an atom. And if you have a different number of protons and electrons, you are an ion. Your protons don't change because they tell you what element you are. So if you lose electrons, you form positive ions, also known as cations. And if you gain electrons, you tend to form negative ions, also known as anions. And then isotopes, again, they have to be for the same element. They'll just have different mass numbers. Some are naturally occurring, while others are radioactive. I thought there was one more in between there. Sorry about that. All right. So the atomic symbol, I just want to review what the different pieces were. And here's a couple of examples of these symbols. X is representing your element, so here we see it as Mg is magnesium. Z is your atomic number, which is just your protons, so that's why we see 12 for both, since they're both magnesium. Mass number is the protons and the neutrons. So in this one here with 24, it would have 12 protons, so the other 12 must be the neutrons. Well, this one has 2 extra in its mass number, so it would have 12 protons and 14 neutrons. And then finally, the top right number, if there is one present, is your charge. Because this does not have a charge, that's telling us it's neutral as an atom. So if it had 12 protons, it also had to have 12 electrons to get a charge of 0. While here we see it's a 2+, you can write this as 2+ or +2. But because it's positively charged, we have that many more protons. So this has 12 protons and 10 electrons. If it had been -2, then it would have had 14. It would have had 2 more electrons than the protons. I'm going to go through and do a couple of examples. Definitely pay attention to whether it tells you if it's an atom or an ion, because that's going to help you in terms of figuring out some of your information. Again, having a periodic table out is going to help you a lot to do this. Fluorine tells us how many protons it has, so if we go and look on the periodic table, we're going to see it has 9. Because it's an atom, it has to have that many electrons as well, because these two have to be equal for the charge to be 0. The complete chemical symbol, again, F would be in the middle. The atomic number, which is our protons, would go in the bottom left-hand corner. The mass number, the protons and neutrons, would go in the top top left-hand corner, 19. And then the difference between the protons and electrons was 0. You could put a 0 here, or you could leave it blank. Isotope name is determined by the name of your element and its mass number, so this would be fluorine 19. Here we're given oxygen as an ion, so we can figure out from oxygen how many protons it has, which is 8. Because it has a -2 ion, we have that many more electrons, those negative electrons, so we would be up to 10 electrons. O would be our symbol's element for oxygen. 8 would be in the bottom left-hand corner for our atomic number. The protons and neutrons would add together to give me my mass number, which is 17. And then the charge, which was the difference between my protons and my electrons, would be -2. So the name of this isotope would be oxygen-17. In the third example, we have 47 neutrons, 36 electrons, and a charge of +1. So if we have a +1 charge, we have that many more protons than electrons, so we have 37 of them. 37 tells me my element, which happens to be rubidium, and it's an ion because we have a charge here. So Rb is going to go in the center. The atomic number, the protons, goes in the bottom left, 37. We add these together to get our mass number, 84. And then we already figured out our charge by subtracting the protons from electrons, plus 1. So the name of this isotope would be rubidium-84. Next we have silver, 108. Silver tells me the number of protons, and because it had a charge of 0, I know it's an atom. So it has 47 protons. Because it was an atom with a charge of 0, it also has 47 electrons. And this number here at the end, its mass number, is the protons and the neutrons. So if we subtract 47 away from that, we get 61 neutrons. So at this point, we should have all the information we need to fill in the symbol. Ag would go in the middle. 47 for the atomic number goes in the bottom left-hand corner. Add these together to get the mass number, 108. And then the charge again would either be 0 or you could leave it blank. So that's part 1 of this review. The next part is talking about average atomic mass. Average atomic mass is similar to calculating an average of in a class if you have certain percentages counting for part of your grade. So atomic mass is the mass of your isotope. That's typically going to be your mass number, but if you're given another mass that's a little more precise in terms of AMUs, you can use that as well. I think that's the way it is on your assignment, so I'll make sure to point that out. And you always want to change your percentages back to a decimal, so you need to make sure you divide them by 100. So you have that percentage of that mass is contributing to your atomic mass. Remember, the atomic masses on your periodic table have decimal places because they're a weighted average based on the presence of the isotopes naturally in nature. So you keep doing that for however many isotopes you have until you've included all of them. So here we have an example with 4 isotopes for chromium. We're given the mass numbers of each of those isotopes, and we're given the relative percentages of those isotopes in nature. So we would take each isotope, for the first one, 50 chromium, multiply it by its percentage, divide it by 100. We would do the same thing for the 52 chromium with the 83.79% over 100. For the 53 isotope with the 9.5 over 100. And finally the 54 isotope, 2.37 over 100. In terms of significant figures, what I want you to pay attention to is that you have multiplication and you have division as well as addition. So we want to make sure we do order of operations, which would mean multiply first and then add. And typically with atomic masses, I'm just going to ask you to go out 2 decimal places. So once I've multiplied across and rounded those to 2 decimal places, I can add them together. And I get that this has a mass of 52.07 AMU, which I think if you look at your periodic table is going to be pretty close to what chromium falls at. And the last thing we're going to talk about is history. Try to put this all together on one slide for you guys. Solid sphere was our initial model with Dalton, how there wasn't anything inside of it. Then plum pudding came along with Mr. Thompson, and that's when we first came up with the idea of electrons, and then the rest of the matter was just positively charged. He determined that using the cathode ray tube experiment. Rutherford came along a little bit later and determined that there was a small positive nucleus, that the positive particles weren't just scattered throughout the atom, which he did with the gold foil, but we still had the electrons, but they weren't moving around yet. And then the rest of the atom really wasn't doing anything. It was known as empty space. Bohr, with the planetary model, first had the electrons in motion. That's the biggest difference between Rutherford and Bohr's model. And then finally, in the quantum mechanical model, we don't have the set orbits. Now we have the generalized orbitals that they can kind of move in whatever orbit they need to be stable, but that they're typically found in certain regions of the atom more than others, and those regions are known as orbitals. A little bit more about the history, just a few guys that we didn't hit on so much in that previous slide. Democritus came up with the original idea of the atom. Talked about Dalton before, but he was the first one to kind of describe what was happening with the atom. And so I've written there the different features of Dalton's theory and how 3 of them are still true today. The ones that aren't, obviously, are that we do have particles inside of the atom, the protons, the neutrons, electrons, and now we know of the quarks. And that atoms of each element are not necessarily the same because you can have the different masses of neutrons, which makes you have the different isotopes. But that we do know atoms of different elements are different because of the different number of protons. No matter where we find a compound at, that compound will always have the same relative amounts of atoms making it up. And then finally, you can't create or destroy atoms. We talked about Thompson figuring out about the electron. Rutherford is responsible not just for the nucleus, but also the proton. Bohr was able to determine that the orbits were in place by the quantums of energy, which allowed the electrons to move from one orbit to another. And Planck was the one that kind of led to the discovery of the quantums, so that helped Bohr develop his planetary model. And then we have the three gentlemen that are responsible for the current model of the atom. Heisenberg, which said you can't determine where something is and where it's going all at once. De Broglie, that you can have particles act like waves, and you can have waves act like particles. And then Schrodinger came up with the addresses, also known as the quantum numbers, the general location where we're going to find the electrons at in the atom. Chadwick was the gentleman who discovered the neutron, and then Millikan figured out exactly what the charge was of the electron with the oil drop experiment. So with that in mind, I know that was a lot of history. I don't really want you to stress too much out about the history. I just wanted to make sure that we touched base on it. I would focus more on the models than anything else, but that was the history that we had done in Chem 1, so that's why I wanted to touch base on it. You definitely want to make sure that you're comfortable doing things like 17, 18, 19. Notice it gave you an exact mass, the 10.013, and boron 11, the 11.009. There's a slight increase in mass in order for the protons and neutrons to kind of stay together in the nucleus. As you can see, it's very small and incidental. But when you are given exact masses, I would like you to use those rather than the mass number for that particular isotope. And then there's just a review of the history. I'm really not going to emphasize history a whole lot, but I just wanted to make sure that we touch base on it again, since that's not something I'm going to talk about in class. All right, and that should get you through review topic 6.